If we want to measure a change in heat in the lab, we're going to do it using calorimetry. The instrument that we use is called the calorimeter. Remember, calories are a common unit of energy or heat. Calorimetry is measuring calories, measuring the amount of heat that's transferred. As we do calorimetry problems, it's going to be important to define two separate things, the system and the surroundings. The system is the substance that you're interested in, that's undergoing the chemical or physical change. The surroundings are everything else involved in the transfer of heat. The surroundings give heat to the system or absorb heat from the system, but the system is what we define everything by. Since processes are defined in relation to the system, in an exothermic process, heat is going out of the system. Remember, exo means out. Heat goes out of the system and into the surroundings. That means the surroundings heat up. Often our thermometer will be stuck in some water, which would be the surroundings. The rising temperature of the thermometer corresponds with the loss of heat by the system. So a process is exothermic when the measured temperature of the surroundings goes up. In an endothermic process, heat goes from the surroundings into the system. Endo means into. Heat is going into the system and it's going away from the surroundings. So the surroundings get colder. You should see your thermometer level dropping for an endothermic process. In the lab, we can use a coffee cup calorimeter, which consists of a couple of styrofoam cups stacked together to create some insulation. And then there's a lid, and we can stick the thermometer down through the lid. There may also be a stirrer placed in there, or you might just stir with the thermometer. The assumption is that the styrofoam cup is able to contain all the heat of its contents. In other words, total heat is constant in the cup. It's not going out or in. We will assume, using the coffee cup calorimeter, that whatever heat leaves the system goes into the surroundings, but not outside the cup. And whatever heat leaves the surroundings goes into the system. There could be a change of heat from the system to the surroundings or from the surroundings to the system, but it would be all completely contained within that cup. We can express this mathematically just by changing the sign on our measurement. The Q of the system equals the negative of the Q of the surroundings. This equation is not saying that the system is always positive and the surroundings is always negative. It's saying that they have opposite signs. This is because heat is going out of one, which would be associated with the negative sign, and into the other, which would be associated with the positive sign. If the system is negative, the surroundings are positive, or vice versa. They have the same magnitude, but opposite signs. If one of them is positive 81 joules, the other must be negative 81 joules. Similarly to the first equation, we could say the Q of the surroundings equals the negative of the Q of the system. If we know the value of one, the other one must have the same value, but opposite sign. Commercial calorimeters work in very similar ways. They are just a little bit more sophisticated. Instead of having styrofoam as an insulator, there are metal containers. Instead of just having a little stirrer, there might be a motorized stirrer. Instead of having just a bulb thermometer stuck in, there could be a digital thermometer. They're just a little bit better in a few different ways, but they're also significantly more expensive.